and she's an avionics engineer at the Hawaiʻi Space Flight Laboratory. She graduated from Waiakea High School and earned her BS in electrical engineering from UH Manoa in 2012. She designs, develops, and operates spacecraft, and she leads the outreach and education projects at Hawaiʻi Space Flight Laboratory. She also mentors students. And tonight she's going to talk about building and operating satellites for remote sensing missions in Hawaii and some of the opportunities out there for students. And she's also going to share a little bit about her personal journey in becoming an engineer. And just side note, after her presentation, there'll be some time for questions. So if you have any questions during the presentation, you can just pop them in the Q&A chat window. Thank you, Amber. You can go ahead and get started.
Awesome. Thanks so much for that introduction, Chris. Let me try to share my screen. Let's hope this works. One of the things we didn't practice. Okay, it's working. Hello, my kako, everyone. My name is Amber Imai-Hong. I'm an avionics engineer and program manager at the Hawaiʻi Space Flight Lab. I'm also the executive director of Ohana Hoku, which is the first Native Hawaiian nonprofit that supports astronomy and space science in Hawaii through community engagement and education. Today, I'm going to be talking about my journey to becoming an avionics engineer, and why the satellites we work on at the Hawaiʻi Space Flight Lab is important to helping us here on island Earth. Okay, so first off, I would not be where I am today without the support of my community. I think my slides stopped sharing. Let's try this again. All right, cool. So as I was saying, I would not be where I am today without the support of my community. It really does take a village, and I'm so grateful to be part of this community and to be a Puna girl. In elementary school, I was labeled as educationally challenged and put in special ed. And I would learn in my late teens that this was the result of me being dyslexic and having ADHD. But this really taught me to embrace STEM, as it was one of the subjects that was less subjective. So there was a correct answer, and I just had to figure out how to get there. While I was at Keao, I met Mr. Art Kimura, who was my vice principal at the time, and he was one of Hawaii's candidates for Challenger's Teacher in Space program, and he really inspired me to, keep dreaming and look to the stars. And that really helped me through my journey. And when I was 8, my mom was confined to a wheelchair due to a neurological disorder. And this meant that I needed to grow to be a problem solver at a very early age. So I had to engineer my way out of a lot of the problems that arose at home. And I pursued every opportunity that I could to learn more about the engineering field, which part of the engineering field I wanted to be in. And this led me to transfer to Waiakea for high school as a freshman in order to participate in the robotics program there, as well as the electric car and all of the other technology programs. I was one of the first graduates of the engineering track that they have there as part of their program. So I participated in FIRST robotics, which is 120-pound robots, underwater robotics, and BotBall, which was fully autonomous robots. So I embraced all these opportunities, and I also worked on electric cars so that I could learn how to weld and do the mechanical side of things so that I could really figure out what area of engineering I wanted to do. I got my first internship as a high schooler at an organization called Joint Astronomy Center. It's now called the East Asian Observatory. And while I was there, I learned about the Akamai internship program. And then I participated in that in 2008 with Canada France Hawaii Telescope in their observatory automation project. Is it gonna go? All right, cool. After high school, I pursued a degree in electrical engineering, and I got a Bachelor of Science in that in 5.5 years. I really struggled with school all throughout, and my parents literally laughed at me when they heard that I had even applied for 4-year schools. I worked anywhere between 1 and 3 jobs while I was in my undergrad to finance my education. And I also applied for every single scholarship that I could, just to try to afford school. Um, on my third day of my first semester, a classmate of mine told me like, "Hey, are you interested in building space robots? I heard you were in robotics." And that's basically how I joined the small satellite team. And that was about 16 years ago, and I've been doing it ever since. Kind of haven't looked back from that. Um, I also started working at the Hawaiʻi Space Grant Consortium in my second semester, and I've been part of the Hawaiʻi Space Grant Ohana for now about 16 years. Um, since I first started, I have worked on 17 satellites and suborbital missions. And of these, we have successfully delivered 4 satellites, and one has made it to space and communicated. So some takeaways from this, I really, for the undergraduates online, take as many internships as you possibly can and get all of the work experience that you can. I found that this was a lot more important than what my grades look like in my transcript. Networking is also really important. The aerospace community is tiny, and everyone knows everyone. So definitely, try to get out there, network. It's not my favorite thing either, but it's something that's absolutely necessary. Also, there's a lot of really cool people, and find mentors. This is really important, and networking is a key way on finding the mentors that you need to succeed. All right, so now I'm going to talk more about my job. So I'm an engineer at the Hawaiʻi Space Flight Laboratory. HSFL was established in 2007, and this was a collaboration between the School of Ocean and Earth Science and Technology and the College of Engineering. So we are the workforce development branch of the Hawaiʻi Space Grant Consortium, and we help to do all kinds of small satellite research. Okay, so we do vertical integration. We do as much as we can possibly in-house. We build and design payloads and instruments. We have an integration and testing facility. We've done all the things for designing and testing small satellites, and we have all the facilities for that, and I'll go into that a little bit more in detail. Next slide. And we also have developed mission operations software. We have ground stations, and we can operate our satellites. So one of the big things that a big goal of HSFL when I first joined was we wanted to be the first university program that could do everything from design through operations and including launch within a university system. No other school at the time could do that. And so it was really cool that we were able to do every single one of those steps. And it's been a great and really rewarding process to be one of the people who have experienced all of the different stages. So our integration and test equipment are shown here. We've got our avionics development equipment and facilities that's pictured on the top right. We've got our clean room where we do a lot of our integration efforts. Our attitude control test facility was $1 million piece of device that we use to test the control systems of all of our spacecraft. We also have our thermal vacuum chambers and the vibration and shock tables. So these help us to better understand the satellites characterize the satellites before they go into space. We find that electronics work differently in a vacuum as compared to sitting on a table in air. So understanding how your satellite works before it gets into space is super important. And the vibration and shock table helps us to ensure that our spacecraft will make it to space and it'll survive the rocket ride. Okay, so why are we building these satellites? Like, what is the point? We're doing remote sensing. So what is remote sensing? It's the science of obtaining the physical properties of an area without being there. So this allows users to capture and visualize and analyze objects and features on Earth's surface or surface of other planetary bodies by collecting imagery. And we use this to analyze and better understand what's happening. So remote sensing can be done on a number of different vehicles. You can use unmanned aerial vehicles or UAVs, weather balloons, suborbital rockets, airplanes and helicopters, or satellites in various orbits. Each platform has its benefits and its drawbacks, including limitations to size, weight, power, the amount of data you're able to collect, the range of flight, altitude, resolution, physical objects being in the way, and other things. There are also a whole bunch of different sensor types, and there's active and passive sensors. Active sensors put out a signal or pulse and detect changes in the return signal. You can think of this kind of like flash photography, where there's the bright impulse from the camera and the sensor that captures the image. And passive sensors are sensors that pick up light that's reflected or emitted off of the objects around you. So that's kind of like your eye. And how do these sensors work? In a lot of cases, we use imagers, so we rely on the electromagnetic spectrum. Typically, we're using the visible and infrared range or spectral bands. At HSFL, we primarily work with hyperspectral imagers, which have lots of narrow bands. There are also multispectral imagers that refer to 3 to 10 bands. This is more similar to like Landsat 8. And why do we care about these bands? We care because all the objects have their own chemical composition, which can be distinguished by their spectral signature. And there are more than 4,000 natural minerals on the Earth's surface, and each has their own fingerprint. The more bands an imager can see, the better the chance of classification. So why do we care about this? With remote sensing satellites, we can learn more about our island Earth. Scientists at Hilo discovered how rapid ohia death was spreading from tree to tree using infrared imaging. And through using UAVs, they were able to track the spread of the virus. We also track our active volcanoes using remote sensing, and we can learn a lot about the chemical composition of the plume and how that changes over time, as well as tracking Mauna Loa to predict when an eruption is imminent. Earth observation satellites have been monitoring the changing Earth continuously since 1972, and the image on the right side of the screen is an image of Kilauea taken by the Terra satellite, which is a NASA-owned satellite. And this is of the ash cloud over, or coming from the Lower East Rift Zone in the 2018 eruption. So here are all of the NASA missions, and the missions highlighted in yellow. I don't know if you can see my pointer. Yes, you can. Okay. The ones highlighted in yellow are the ones that HSFL is participating in. So most of the ones around here, these are the Earth observation spacecraft. The ones near this moon here is the moon sensing. Many of them are related to the Artemis missions. We've got the deep space satellites out here and the sun monitoring satellites here. So these are all of NASA's small satellite and fleet. And HSFL has been very lucky to participate in several of these missions. And I'm going to talk about that. So back to the research done at HSFL. We help to support remote sensing missions that includes Earth observation, particle physics, and solar physics. And that helps us to better understand what's happening here on Earth and to characterize that data and how the space environment affects life here on Earth. We're also looking into exoplanet research by taking Earth observation technology and sensors and turning them around to look in the opposite direction into deep space. So HIGP was the first satellite that we delivered. This satellite was launched on the Super Stripey rocket off of Kauai, and that was in 2015. The satellite itself weighed 55 kilograms or 110 pounds-ish, and it was about the size of a small mini fridge. On board, the main payload was SUCHI, or the Space Ultra Compact Hyperspectral Imager. This was generation 2 of this sensor, using a Fabry-Perot interferometer, sorry. The next satellite that we delivered was called Neutron 1. It was a 3U CubeSat. The primary payload was a neutron detector that was assembled by the Arizona State University. This sensor was a flight spare for the Lunar HMAP mission to the moon. So they wanted to test to make sure that their sensor worked while it was closer to Earth, so that we could kind of characterize it in a space environment. This project took about 5 years to deliver, and I think over 150 people worked on this one mission. The satellite itself was deployed out of the International Space Station in November of 2020. Delivering a satellite during COVID was a completely different piece that we did not know how to deal with. It was very interesting to have to do a lot of the integration and testing while the team was physically separated. So we'd have a couple people in the clean room, masked up and stuff, and the rest of the team would be at home trying to instruct the others how to complete the tests, and what to do, how to troubleshoot things while we're not all in the same area. Also, getting satellites to their launch, or to the launch provider, was completely different. Normally we would pack it in a Pelican case, buy the satellite its own ticket on an airplane, and fly it over with escort it onto the airplane and take it there. We couldn't do that, obviously, with all of the flight restrictions, and so what we had to do was ship the satellite using Aloha Air Cargo from here to LA, and then we had to use a white glove service from FedEx to take the satellite from LA, drive it straight to the NanoRacks facility in Texas, where they integrated it into its launch pod, and then from there it was driven again in its launch pod this time to Wallops Flight Facility in Virginia, where it was then launched to the ISS on a resupply mission. I think I have some pictures. Here we go. So this image down here is from the integration of Neutron 1. Neutron 1 was a 3U CubeSat, so it's about the size of a loaf of bread, and it gets packed into this launcher pod here. Then everything gets wrapped in bubble wrap and put on the payload bay of this rocket. The rocket then goes and connects with the ISS, and the astronauts take this pod here and load it into the deployer mechanism. Then when they press a button, a latch releases, and the spring system pushes the spacecraft out into space. And so this image here was taken by an astronaut that was on the ISS while Neutron 1 was deployed. Neutron 1 was on orbit for about 20 months, so deployed in November of 2020. It was promptly hit by a bunch of radiation, and we lost contact with it for about a month before we regained contact with it in late December. So it was kind of our Christmas miracle, because we were hunting for the spacecraft via amateur communications on UHF bands for almost an entire month, where we couldn't hear anything. Neutron 1 deployed with 2 other spacecraft, and the first spacecraft, it changed their frequency. So they had to figure out what frequency it was at and then contact it and then resume their mission. The second mission, the last message they got from it was that it was going into deep sleep mode, and they never heard from it again. And then we also had a little bit of ambiguity in our modeling. We thought that Neutron 1 would deorbit around January or February, of 2022. But because of how heavy Neutron 1 was, as it was falling around the Earth, it had more momentum than the other two spacecraft that it deployed with. So it continued to fall around the Earth until June of 2022, whereas the other spacecraft burned up a lot sooner than that. The current mission that we are working on right now is HITI, or the Hyperspectral Thermal Imager. This is one of the NASA-funded missions, and it will demonstrate hyperspectral imager in a CubeSat platform. So this is the fourth generation of the instrument that's being developed, and so Hyakisat had version 2. There's been another version in between, and then HITI will have version number 4 of the same instrument. So this is what a 6U CubeSat looks like when it's in its pieces. So before we stack everything together, we put this on the bench and we tried to test all of the systems. So we've got all of the different components. We've got our reaction wheels here that helps to orient the satellite. We've got computers. This computer back here is the Unibap IX5 computer. This flight computer is our payload computer, and it processes all of the data. The computer itself costs about $350,000. Spacecraft are not cheap. So that was one of the things that we had to get over while we were working on this. So yeah, a lot of these components are very expensive, and it was definitely a lot of trial and error as we all learn together as a team what works and what doesn't as far as spacecraft integration goes. We've learned a lot that we need to be very careful when we're integrating things. A lot of components have these thermal conduits. So basically this is connected to ground, and it just tries to pull the heat off of the board. But that also means that if you short something to that, it could burn up your boards because you have a reverse current. So being very careful, checking, double checking, getting someone else to double check you, all very important. So this is what HITI looks like when it's fully assembled. We've got some of the students on our team who have been helping with this integration. But yeah, this is the HITI is about the size of a shoebox. It's a 6U CubeSat. And so it is fully integrated. We are hoping to deliver this in December of this year. And then it should be launched sometime early next year. And then hopefully be on orbit by the end of Q1 or beginning of Q2 of next year. So we're very close to delivering this this project. We are currently on year 5, I believe, of a 2-year project. So we're ready for HITI to, you know, be out in space and collect data. One of the big things that it'll prove is that this hyperspectral imager works, and that satellites similar to Landsat could be done in a smaller form factor. So the Artemis CubeSat kit is a 1U satellite that has all of the basic components necessary for aerospace, for flying things in space. So this project was funded by NASA in 2020 while we were all in COVID lockdowns. So a lot of the times we were meeting as a team on Zoom. One of the big challenges here is that NASA needed a foundation enabler to train the Artemis generation. So we developed this 1U CubeSat kit that has power, onboard computer, and all of the things necessary to just connect a payload and fly it in space. The satellite design has 33 millimeters of vertical payload space, so it's about 1/3 of the 1U CubeSat for a team to insert their own payload. We've had a couple different student teams through various programs insert technology demonstration payloads like radios, as well as neutron detection or high energy particle detectors into this CubeSat. It hasn't flown in space yet, but we're hoping to get it into space sometime next year. Along with this hardware kit, we've also implemented 2 different open source software. We have Cosmos, which is the comprehensive open architecture. Oh, I shouldn't have started this. Cosmos is a software that we've used on all of our spacecraft missions at HSFL. It was developed by several of the software engineers at HSFL, and they are spinning off a company called Interstel, where they're hoping to market this in a freemium model. So we've integrated that as well as F Prime, which is a NASA JPL based open source software platform. We also have integrated a online course for this around this kit. So we have an online textbook as well as interactive labs and a curriculum to follow. So for teams that don't have a formal aerospace program, they have all the resources that they need to be able to assemble a satellite and put it into space. So we are trying to reach all of the states that have not yet put or launched a CubeSat through the CubeSat Launch Initiative. So that was one of the big goals of this program. And we have done this mostly with a student team mentored by HSFL engineers. The spacecraft itself was designed to withstand it was designed to meet all of the requirements for a CubeSat launch initiative. It was tested to unmanned standards, so rockets that are unmanned are allowed to vibrate a lot more. So we tested it to NASA Gev's acceptance levels, and we also designed it so that the rest of the system was safe enough to fly on manned missions, which are a lot more stringent because the safety of humans are involved. So project outcomes, like I said, this project started in May of 2020, and we are here on about month 40 of our 1-year project. We've had over 70 faculty, staff, and students that were supported in the development and testing of the Artemis CubeSat kit. This includes the hardware, software, and the educational materials and documentation. We've dabbled a little bit in the K-12 space through Project Poke, and partnered with a local nonprofit, Sunworks, to host a hackathon design challenge for high school students, in which over 90 students from all counties of Hawaii participated. This project has generated 2 papers and 4 conference presentations, and so far 7 kits have been delivered to end users, and we've integrated their feedback into the design as well as the documentation. So how can you be involved? So we have a lot of opportunities for undergrads to work with HSFL. As I said, we are a workforce development branch of the Hawaiʻi Space Grant Consortium. So we do promote their university research internship program. We've worked with a number of students on suborbital projects, various testing capabilities, as well as development of payloads and sensors. Another thing is the EPIT program. So HSFL supports the Earth and Planetary Exploration Technology Certificate program. So there's 4 courses in the EPIT program, and students learn about planetary missions. They work with engineers as well as scientists all together, and they're able to build a satellite and propose to the CubeSat Launch Initiative at the end of their program. So we're hoping to fly multiple missions. I think right now we have VIACES, which has a launch. They were selected for a launch, and there's also the CRAPES payload, which is working towards that. So HSFL engineers are working with students on these things, and we're hoping to be able to improve this program as well as move it into a minor program before it becomes a full aerospace program and major at UH Manoa. The EPIT program is currently run through the Hawaii Institute of Geophysics and Planetology, and it is cross-listed as the aerospace track of mechanical engineering. And that's all of my presentations. Thank you so much for listening.
Mahalo, Amber. You have like the coolest job. So cool.
Thank you.
Satellites in space. Let's see if I don't see any questions in the chat window yet, but I was curious, have any of the Artemis CubeSats been launched into space that you know of?
Not yet. So one school did vibration testing. I don't think they launched it. I haven't heard back from them, but I know they did vibration testing on it and they mounted their own payload inside of the structure. They didn't mount it well, so it ended up coming loose during their vibration test and it was kind of banging around in there. So we found that we over-designed the structure. Also, one of the attendees on the call had stood on top of the structure, so we know that we've over-engineered the structure. It holds more weight than it needs to and is a lot stronger than it needs to be. And the electronics are well packaged, so nothing breaks when it goes through extreme environments, let's say. But we haven't successfully launched anything yet. We haven't attempted. We're hoping to do so within the next year through the vertically integrated project through Aerospace Technologies. We have a group of about 15 students right now that's working to integrate a radio payload into the 1U structure. And then the goal for the end of the semester is to have everything in the satellite, and then we'll do environmental testing on it, and then hopefully get a launch for it in the middle part of next year. And in order to get a launch, we need to procure one. So that's about $40,000. And we also need to pay a licensing fee to the FCC and get approval from both the IARU as well as the FCC. So we've got a journey ahead of us, but it's something that we're actively working on.
Awesome. Yeah, spaceflight is not cheap, but it sounds like you've got a really robust satellite kit put together. This is our Q&A time, so if you've got any questions for Amber, go ahead and put them in the chat window. I have another question, more about kind of the path you took to become an engineer. I guess what do you think was the most important thing for you in like your initial steps in taking aerospace engineering classes? Like if you could go back and talk to your younger self, like what would you tell her?
Okay, so UH is one of the schools that doesn't have a formal aerospace program. I think only 17% of schools in the US have an accredited program. But in the start of my journey, I think I needed a lot of encouragement. I wanted to give up so badly multiple times in my career as a student. And so one of the things that one of the pieces of advice that I got from my mentors was don't give up. You can do this. And just to like focus on school a little bit more. I was very involved in the robotics programs in Hawaii, and I spent a lot of my weekends and my downtime working on volunteering for a bunch of the programs. I wasn't the best student, but honestly, working with the students that I did and mentoring them and actually seeing a lot of the students grow up from elementary through college now is super rewarding for me. And so that kind of helped to keep me going. But yeah, focusing on school was a piece of advice that I probably would have given myself. A good piece of advice that I did get as a middle schooler, I think, was to start networking early. So I started talking to engineers and professionals in various fields just to get a better understanding of what I wanted to do.
So we've got a few questions coming in the Q&A right now. Thank you for sharing that. It sounds like perseverance and hard work and focusing on school and then finding the things that were rewarding for you were all definite motivators. So let's see. First question is from Ian. He's asking, can you explain a little bit about low orbit versus other orbit missions? Like, what's the difference between the two?
Okay, so low Earth orbit is from like just above the Earth's atmosphere to I think about 600 kilometers. I'm not 100% sure, but there's low Earth orbit, there's mid-Earth orbit, and then there's geosynchronous or geo orbit. So as you get farther away from the Earth's atmosphere, or from what protects us here on Earth, you are exposed to deeper space, so the temperature swings are way bigger, and you also have to deal with a lot more radiation. So how does that affect the satellite? Electrical components only work at certain temperatures, so you have to make sure that your thermal system is up for it. You also have to make sure that your electronics are radiation tolerant, or they're going to survive longer, because radiation particles can cause latch-ups. It can cause your satellite to fail completely. So it kind of depends how the radiation hits, and it's almost completely random. So it is really challenging to work outside of low Earth orbit. Another thing is that for satellites that are in geo, they need to be able, like, they need to have some sort of propulsion system to get them to graveyard orbit. So to get them out of orbit, one of the things I didn't talk about much is the FCC has a rule that you need to deorbit your satellite within 5 years. That's a very new rule. It was implemented, I think, last year. And so there's various challenges. So a small satellite like a 3U or a 1U at the upper end of the low Earth orbit would have a much harder time deorbiting within that time frame. So propulsion is necessary, which is something that we haven't implemented on any of our spacecraft as of right now. So these are some of the different challenges that we have to deal with when we deal with different orbits, different geometries, and different even different altitudes within low Earth orbit.
A lot of considerations there. Where are the satellites actually being launched from and how?
So satellites are we've launched Hyakosat, which was our biggest satellite that we've physically delivered. That one was launched from Kauai at the Pacific Missile Range facility. We have a launch site there, and that was launched on the Super Stripey rocket. We helped to design the rail launcher for that as part of HSFL. And the rail launcher was that was for the largest rail launch sounding rocket that was supposed to get into low Earth orbit. We only exercised that one time, and statistically, first launches just don't go well. So there was something that happened, a failure in the first stage. So the satellite ended up becoming a submarine, because the rocket ended up going into the ocean just south of the Big Island. Some of the other satellites that we've launched, so like Neutron 1 was launched out of Wallops Flight Facility, that's in Virginia. So they were launched on a Northrop Grumman mission as a resupply mission. So that's really nice when we get a resupply mission, because the satellite gets wrapped in bubble wrap inside of its deployer pod. So it has a very nice smooth ride going up to space. Whereas if like the Super Stripey rocket, you don't have that. It is shaking a lot because there's no humans on it. I think we've also we launched HIAPO, which is the Hawaii Science and Technology Museums. They want to launch on the Firefly Alpha, the very first launch. And so again, first launches don't go very well. But that was launched out of Vandenberg Space Force Base in California. So we ride on whatever ride share is available. There are a lot of newer companies coming out that are purchasing a ride on a rocket and then kind of selling space on that. So the aerospace industry has changed significantly since I first got into it in 2007. Before you were working directly with rocket companies, you were using things called light bands to release satellites, and now we're talking deployer pods and just having an astronaut press a button to release your satellite into space. So satellites are launched on a rocket to get to space, and then it's deployed using a deployer pod with pretty much spring actuated.
Next question comes from Heather. She's wondering, what advice would you give to college students at other universities who may not have aerospace and engineering programs after school?
So if they're interested in aerospace or doing space missions, definitely take a look at our textbook. It's a good introduction on how to design a spacecraft mission. When we had high schoolers and middle schoolers go through the steps of designing their own mission. And then several of the attendees are currently in the EPIT program. So they're walking through that mission process, like how to design a mission, what's important, what are the basic components of a spacecraft. Yeah, there's also a lot of really great resources on NASA's website. There's the CubeSat 101 document. And yeah, just talking to people has been super helpful. I've been in this industry for a while, but I think a lot of what I've learned has been by talking to professionals who have done lots of space missions. And it's always hard. Honestly, doing projects and tinkering is another thing that I think is super important for college students who don't have the guidance for like directly associated with the aerospace engineering program. Like if you can, pick up a Raspberry Pi or pick up an Arduino, start tinkering and learning how all of the sensors work and how you can connect them together, super important.
We at our PISCES website, pacificspacecenter.com, we have a student resources page that has opportunities for high schoolers and undergrads to get involved in aerospace projects. A lot of them are put on by NASA, but that's another resource that you can look at for getting aerospace related experience. Next question: Do you have any are there any big projects that you dream about doing?
Oh, big projects that I dream about doing. Honestly, one of the things that HSFL as a whole has been dreaming of is like getting a moon mission, getting out of low Earth orbit. So far, what we've been doing is doing low Earth orbit missions. Personally, one of the things that I would like to see is expansion of the aerospace industry in Hawaii. I think that aerospace, like Hawaii, is one of the best places to do aerospace. We are the furthest south of all of the states, and so we are closest to the equator. And we would be able to get a lot more payload to space if we had a launch facility here in Hawaii. I know it's quite controversial, and there's been talk of it for years, but I do want to see, like, if we were talking about big projects and things that I dream of, is that just having a bigger aerospace presence here in Hawaii.
Does HSFL have a long-term goal to get a satellite or some kind of spacecraft to the moon? Or is that kind of like way down the line, like beyond planning right now?
It is definitely something that we're looking at. We're looking at deep space missions, moon missions, and we're trying to work on our electronics and trying to find electronics that would be safer in a higher radiation environment. So it's something that we're actively looking at.
Very cool. Let's see, next question. What are the biggest collaborations taking place between like HSFL and others?
So we collaborate with a number of different private entities, universities. We collaborate with pretty much whoever comes and approaches us. So one of the big collaborations that we're hoping to get, we're applying for a or we're putting out a proposal for a spacecraft that will do solar research with IFA. So we've been partnering with IFA recently. We also have projects that are more ground station related with various military contractors, NAVFAC. We've been working with the NPS, Naval Postgraduate School. We collaborated with ASU on Neutron 1, and we're currently working on HITI 2, which is the next generation of the HITI instrument. Essentially, we want to have that instrument on as much as possible, whereas HITI will run only over the continental or the lower 48 of the continental US. So we want to increase the duty cycle of the instrument for HITI 2. And so we're looking at a 12 to 16U spacecraft. And for that, we're collaborating with ASU. We also partner a lot with JPL, NASA Ames, a lot of the NASA facilities. And we've worked with Sandia National Labs. But we've tried to partner with Los Alamos National Labs as well. So we've been we're a very small team. There's like 10 of us on that are either staff or faculty at UH, and but we do try to collaborate with anyone who has a project and is interested. We've also done some drone work, so we have collaborated in the past with UH Hilo. I actually got to fly with Drone Team 1 for the Lower East Rift Zone eruption in 2018. So we collaborate with whoever we can, whoever approaches us. So if anyone has ideas on who we could partner with, we're always open to that.
Next question is, how do you coordinate with other satellites in lower orbits to prevent collisions?
Ooh, collision avoidance. That's a fun one. So we have on board an attitude control system, so we can do a little bit of movement of the satellite and orienting of the satellite, but we can't really like avoid any satellites because we don't have a propulsion system. There is the 19th Space Command, I think. They're part of the Space Force. They monitor everything in space, and a lot of it is to protect the ISS and manned rockets that are going up into space. They track everything that I think is 2 centimeters in size or larger. And so they let us know as operators if our satellite is on track to collide with another satellite, and they try to, or not even a satellite, if it could be just a piece of space junk. And they try to work with everyone who's involved to maneuver the spacecraft so that they don't collide. In the 20 months roughly that Neutron 1 was in orbit, we only had 1 near miss. So everyone says that space is really crowded, and in a way it kind of is. It's getting worse, but the likelihood of collisions is not that high. And a lot of material selection goes into making sure that should your satellite collide with another spacecraft, you don't create a giant debris cloud that impacts other spacecraft as well. So those are all considerations. And then on top of that, we also have to consider the spacecraft needing to burn up in the atmosphere, because the way that we deorbit our satellites is by burning it up in the atmosphere before it gets to anywhere where there's humans. So we need to make sure that the particles are small enough such that no one gets hurt.
Interesting. So what's considered a near miss? Like how close is a near miss?
I think for Neutron 1, it was about like 3 feet or so. Or like, yeah.
That is really
it was pretty close. I could be off by a factor. I think it was either 3 feet or 3 meters. I can't remember, but we were relatively close to colliding with another satellite. We had no control over moving the satellite though, so it was we were notified after the fact also. There was some miscommunication with paperwork, but when we delivered HIAPO HSTM satellite, we had to put in specific paperwork that said, this is like, I am the owner of the satellite, here's my call sign, here's my contact information, so that should that satellite have gotten into a near miss situation, they knew who to contact.
Okay. About 3 feet in space is like really.
Yeah, zooming right.
Oh, here's an interesting question. How do you manage altitude control without propulsion?
Oh, so attitude control without propulsion. So yes, a lot of it is we have magnetometers, we have reaction wheels, um, torque coils. So torque coils are essentially electromagnets that we use to align the spacecraft with the Earth's magnetic field. So it's not going to put you in a different orbit. It'll just reorient the satellite in a different direction. For bigger motion, we would use the reaction wheels, which if you've ever held a motor and felt that pull, that pull is what pulls the spacecraft. And in space, you don't need a lot of force to move the satellite. So the reaction wheels are relatively small. They're about an inch, a little over an inch in size. They are precision milled so that it evenly pulls. That's one of the things that university teams have a hard time replicating. We purchase our attitude control system from a vendor in South Africa. They're called CubeSpace, and we really like working with them.
Has there been any considerations for offsetting carbon emissions in their space missions?
Um, it's something that we definitely think about. So one of the things that has been kind of interesting and has been floated around is using a glider or towing a rocket up past like into Class A airspace, and then launching the rocket off of either the space or off of the airplane or off of a glider. Of course, unmanned gliders are probably the most are safer, and some of these gliders can be powered using primarily solar power. So that's something that we're thinking about. If you can get it to Class A airspace, I think it reduces the amount of fuel that's needed by about 70%. I could be wrong on that number. It's been a while since I've looked at the numbers for that, but yeah, that's kind of one of the ways that we're considering it. Most of the fuel is used up just trying to get from the ground up to Class A airspace. And the reason for that is there's a lot less air resistance once you get past a certain point because there's a lot less air.
Interesting. That makes sense. Okay, another question is how challenging is thermal management on these 1U and 3U size satellites?
Thermal management is a pain. Even thermal modeling is a pain. It is definitely a challenge. So a lot of the processors use a lot of power, so they give off a lot of heat. I know if you look in your desktop computer, usually you see like the processor has this giant like spiky thing coming off. That's the heat sink. So it's trying to use the air around it to cool. In space, you don't have that option. So you have to put some sort of metal in contact directly with the processor and then with a structural element that has the potential to not be looking at the sun, to be colder, at a colder potential. So it spreads out that heat a lot more. But in a compact system like a 1U or a 3U, the chances of shorting something out or just, it's really hard when you're trying to pack everything in very densely. So it is super challenging. I mean, even for HITI, which is a 6U CubeSat, we have radiator panels, and that's the thing. The bigger the spacecraft is, the more components you have in it, so the hotter it gets. So thermal management is a huge, trying to solve that problem is huge. So for HITI, we have a component that will literally overheat in 7 minutes on the bench top. And we have radiator panels that we tested in the thermal vac chamber just to be sure that while we're operating in space, we can actually dump the amount of heat we need. Because we've got a number of components that heat up a lot and that need to be at a lower temperature. HITI also has a cryogenic cooler on board, and so that generates a lot of heat, and it also needs to be at a specific temperature in order to hit the calibration temperatures that it needs to be at in order for the instrument to operate. So lots of fun challenges with thermal management. Right now we have mostly passive, or we have all passive thermal controls. So it's we are using heat sinks and radiator panels on everything, but definitely looking at how to manage heat better as we get into larger spacecraft like 6U or 12 or 6U, because that's definitely going to be another issue.
Thank you, Amber. We have one more question. You mentioned that students tested the CubeSat structure, and the student is wondering what was the outcome of that experience? Actually, this is a two-part question, so that's the first part of the question.
So we have this, one of the labs within our textbook is to have the students test the satellite structurally. So we have the simulation model of what how much weight this spacecraft should be able to hold. So the students were able to put a flat structure on, or they put a table on top of it, and then stood directly over the spacecraft. And with a typical student, I think the satellite is able to hold about 170 pounds or so. So we've had students stand on top of it. So far, we've only had one structure break on us, with the 3 cohorts of EPIT students that have gone through the course. And the reason that it broke was because one student was standing on top of it, it was fine, and then they tried to put another student on top of the structure, which was already over the limit of what it was supposed to be. And then the structure tipped a little bit and fractured. What was very interesting was that it fractured in the spots where the model said was the weakest. So we proved that the model was correct.
The second part of the question is more about your own studies. The question is, what motivated you to pursue aerospace, and what are some of the kind of long-term goals of being in an aerospace track?
So I really like doing instrumentation. I learned that like I learned that I like tinkering with stuff. I learned that I like playing with sensors. I learned this through robotics in high school, through my internship at Joint Astronomy Center and at Canada France Hawaii Telescope, as well as some of the work I did developing sensors for Seymour, which is part of SOAS. So I started like tinkering with stuff, and then I realized that I really liked that. So I stuck with instrumentation. Basically that means I work with the scientists to make their payloads or make what they want to test fit into the spacecraft. So that's kind of one of the things like that motivated me was my interest. Like I like playing with other people's expensive toys. And what was the end goals? I really wanted to do something that could be done in Hawaii. Like I didn't want to leave Hawaii. This is my home, and I didn't particularly want to live on the continent. And so I thought that aerospace was a way that I could stay here, and I thought that it's it's cool. I love working in the space industry. And I love meeting people who work in the space industry because they're usually really awesome people. But yeah, I really wanted to grow the aerospace industry in Hawaii. So that was kind of some of the end goals of being in that track as far as studying. But yeah, that's what we're trying to do both at HSFL and personally.
Thank you, Amber, so much for being with us tonight. That's all the questions we're going to do for now. Yeah, I really appreciate you sharing your knowledge and experiences and kind of all the ins and outs of the engineering work you do. And thank you, everybody, for joining us. I hope you have some valuable takeaways from tonight's talk and feel a little bit more inspired about technology and some of the opportunities that are available here. We are holding another space science symposium coming up on November 14th. It's going to be on a Tuesday in the afternoon at 3 p.m. If you're interested in attending that one, you can sign up for our newsletter at pacificspacecenter.com, or follow us on social media. We'll have announcements on there too. For that talk, we're going to be featuring Yahaira Sierra Sastre, who is a Puerto Rican scientist, educator, and aspiring astronaut who works for Blue Origins, which is Amazon founder Jeff Bezos's company. So we'll have a registration link for that by next week if you're interested. So yeah, big mahalo again, Amber, for joining us tonight and sharing all your experience. And thank you everyone for joining us. Have a great night. Mahalo.
Thank you.